Welcome to the AudioML Papers podcast. So we've landed in the third week of October 2025, and if you're keeping tabs on AudioML like we are, you can feel a shift happening.
Oh, definitely.
It feels like we're really moving past just, throwing bigger generic models at problems.
Yeah, the trend is clear. It's towards these more sophisticated, high-integrity, domain-aware solutions. Today's papers really underscore that.
They absolutely do.
It does. That common thread, running through these three, it's this deliberate push to embed real domain knowledge.
Like actual physics or linguistics?
Exactly. Linguistic structure, acoustic physics, even clinical insights, directly into the architecture or the training itself. So our mission today isn't just a summary.
Right.
We want to really unpack the key architectural ideas, look at the clever training techniques. Some are physics-informed, which is fascinating, and maybe gauge how long these ideas might stick around for your research.
Okay, so we've got three pillars for this deep dive. First up, text-to-speech, TTS, with a pretty novel Tokenizer-Free method.
Very interesting one.
Then spatial acoustics, where, like you said, physics meets neural fields.
Yeah, implicit neural fields.
And finally, a really significant step in clinical speech assessment, using an unsupervised approach. It really feels like a snapshot of the fields growing up, moving beyond just, basic deep learning.
It is. And what's really cool is how each paper directly attacks a core problem from earlier, maybe simpler methods.
Okay.
They're all architecturally responding to things like error accumulation in TTS or spectral blurring in acoustics or maybe data scarcity in the clinical world. If you want a sneak peek at what the next generation of audio models might look like, well, this is probably it.
Okay, let's dive into paper number one. This one tackles that quantization ceiling that's been a bit of a headache for generative audio folks.
A major headache.
It's called VoxCPM. Tokenizer-free TTS for context-aware speech generation and true-to-life voice cloning. Authors are Yixuan and colleagues from Tsinghua University. Popped up on Archive, pronounced Archive, September 29th, 2025.
Yeah, and they really nail what they call the fundamental trade-off in speech synthesis today. You've got systems using discrete tokens, right? Usually from pre-trained things like VQVAEs. And those are stable. They scale okay, but they hit that ceiling, the subtle stuff, the expressivity. It gets kind of flattened out when you force everything into a fixed set of codes. You get that slightly robotic sound sometimes.
Right. And the other way, the fully continuous signal approach, that's where you get the error accumulation problems, isn't it? Why does that happen exactly?
Well, it's because you're basically asking one big model, often an LLM, to do two very different jobs at once.
Okay.
It has to do the high-level planning, like the overall prosody, the global stuff, and at the same time, it has to do the low-level acoustic rendering, actually making the sound waves second by second.
So it gets pulled in two directions.
Exactly. The model often gets bogged down trying to perfectly match the local acoustic details, the texture. And when it does that, the high-level coherence, the meaning, the long-term stability, it starts to drift. The tasks get entangled and the model struggles.
So the VoxCPM folks figured the real issue wasn't just the training. It was this architectural entanglement.
Precisely.
And their fix is this hierarchical semantic acoustic modeling using semi-discrete residual representations.
Sure.
Okay, how does the architecture actually pull that off while staying end-to-end?
Right. The kind of secret sauce here is this differentiable finite scalar quantization bottleneck, FSQ. Now, it's really important how this is different.
Okay.
Older methods like VQVAE, they use quantization to create hard, discrete targets for the model to predict.
Right, like predicting token number 57.
Exactly. But that often pushes you towards using lots and lots of dimensions for the quantization, and you get this vocabulary explosion, just too many possible tokens.
But VoxCPM isn't using the FSQ output as a prediction target.
No, that's the key insight. They use the FSQ bottleneck purely as a regularization step. Because it's differentiable, it can be part of the backprop. It gently nudges the high-level hidden state, the semantic meaning, to cluster into more stable, discrete-like zones.
Without needing a hard target or some external pre-trained tokenizer.
Exactly. It stabilizes the high-level stuff internally.
So this constraint sort of forces the architecture to specialize. Tell us about the two parts that emerge.
Yeah, the separation becomes really clear in the architecture. First, you get the text semantic language model, or TSLM. It's stabilized by that FSQ bottleneck, and its job is just the semantic prosodic planning, the slow, long-term stuff. That gives you stability.
Okay, the what and the how globally.
Right. Then second, you have the residual acoustic language model, the RAM. Its only job is to reconstruct the fine details, the acoustic nuances, basically. The residuals that got smoothed over by the FSQ step.
So it adds back the expressivity.
Precisely. It handles the high frequency stuff, the speaker-specific timbre, all the richness that the TSLM ignored for stability.
And the really neat part here is the training. No complex multi-stage pipelines, no relying on separate pre-trained tokenizers.
Yeah, the whole system, even though it has these specialized parts, is trained fully end-to-end. Just a single, pretty standard diffusion objective.
Wow.
So you get that functional separation you need for good quality speech, but without the engineering headache and brittleness of combining separately trained models. That simplicity is a really big win.
Okay, let's talk scale and performance then. They train this on a huge data set. 1.8 million hours of bilingual data.
Massive.
And their 500 million parameter model hits state-of-the-art for zero-shot TTS among open-source systems. That scale alone suggests they must have tamed those stability issues you mentioned.
It does. And critically, they show it's practical, too. They quote an RTF, real-time factor, of 0.17 on a consumer GPU, and RTX 4090.
So it's fast enough to actually use.
Yeah, it's not just some theoretical model, it's deployable. And, longevity in ML often comes down to practicality. VoxCPM seems to have that.
You mentioned figure 2 earlier, the TS&E plots. That's where they really show the separation works, right?
Absolutely, that figure is crucial. It's the visual proof. You look at the TSNE for the TSLM FSQ part, and you see clear clusters based on semantic content sentence, meaning overall tone, things like that.
Proving it learned the high-level plan.
Exactly. Then you look at the ROM residuals, and the clusters are totally different. They separate based on speaker identity and tiny acoustic details. It visually confirms they successfully disentangled the high-level meaning from the low-level sound.
Okay, I have to push back a bit here, though. 500 million parameters, this massive data set, this elegant concept. Why only 16 kilohertz audio output? I mean, high-end applications, even research, are looking at 24 kilohertz, maybe higher now. Is this just a super complex way to get audio quality that feels a bit dated?
That's a really fair point, especially if you're thinking about commercial use right now. The 16 kilohertz does feel a bit behind the curve, but I think you have to view the core architectural innovation as the main takeaway here. My guess is they prioritized cracking the fundamental structural problem, first getting rid of the tokenizer dependence, achieving that clean disentanglement. Pushing to 24 kilohertz or 48 kilohertz, that probably needs significantly more capacity in the realm, maybe more complex diffusion steps, definitely more data crunching. They might have deliberately chosen to solve the structural issue first.
No, the longevity isn't about the current 16 kilohertz. It's about the blueprint.
Exactly. The blueprint for using differentiable quantization internally as a regularizer, not an external target. That's the idea that will likely persist and get built upon. Even when the next version hits higher sampling rates, it shows a path forward.
That makes sense. The concept is the breakthrough. The specs will follow.
I think so. They've shown how to tackle that entanglement problem head-on within a unified framework. That's powerful.
All right, let's switch gears completely. From generating speech to modeling how sound moves in space. Our second paper is INFER, Learning Implicit Neural Frequency Response Fields for Confined Car Cabin. Yeah. By Harshvardhan Thakawali, Nirupam Roy, and Phil Brown from University of Maryland. This one came out October 8th, 2025.
And this dives into a really tough engineering challenge. Modeling spatial audio, especially in tricky spots like a car cabin. It's notoriously difficult.
Why specifically cars?
Well, you've got really complex sound reflections, modal behavior, because it's a small enclosed space. You have all sorts of materials, glass, leather, plastic, all absorbing and reflecting sound differently. Plus, it changes constantly, right? Passengers move, windows open.
Right. And the old ways, like simulations.
Traditional methods like ray tracing or finite element analysis, they get computationally very expensive very quickly. And often they just don't capture all the real-world nuance accurately enough.
And importantly, those kind-of-main methods often mess up the spectral details, right?
Yeah.
Especially phase.
Yeah.
Leading to kind of blurry spatial sound.
That's a huge problem. They struggle with frequency-dependent effects, which is precisely why INFER takes such a different approach. The core idea is to work entirely in the frequency domain, using implicit neural representations. So instead of simulating wave propagation over time, it learns to directly predict the complex frequency response, basically the transfer function, between points in the space, frequency by frequency.
Avoiding that time domain averaging or blurring.
Exactly.
So what's the neural network actually predicting? Is it just how loud the sound is at different frequencies?
It's more sophisticated than that. It predicts the complex attenuation. That's crucial. The paper says it predicts the complex attenuation encoding the frequency-dependent transmission loss at point P and directional spectrum re-radiated from that point toward direction N.
Okay, complex meaning.
Meaning it includes both the magnitude, how much the sound is attenuated, and the phase shift at each specific frequency. And getting that phase right, especially at lower frequencies, is absolutely critical for our brains to figure out where sound is coming from. The frequency domain is the natural place to model that accurately.
This really does sound like blending deep learning with hardcore acoustic physics.
Mm-hmm.
You mentioned earlier something really elegant, embedding physics using Kramer's Kronig constraints. Why is that specific constraint such a big deal for a model like INFR?
Okay, yeah, this is where the paper gets really clever, and it's a great lesson for anyone building physics-informed neural networks, or PNNs.
Right.
When you model any kind of response function, like an acoustic transfer function, there are two parts. The attenuation, which you can think of as the real part of a complex number, and the dispersion, or phase shift, the imaginary part. Now, a standard neural network just trained to minimize error on data.
Yeah.
It might find a solution where the predicted attenuation and the predicted phase shift are individually accurate, according to the data, but together they describe a system that's physically impossible, like it violates causality.
Meaning sound would arrive before it was sent.
Essentially, yeah. It could predict a phase response that simply cannot exist in a real causal physical system, even if the magnitude prediction looks good. The Kramers-Kronig relations are fundamental physics. They state that for any linear, time-invariant causal system, the real part, attenuation, and the imaginary part, phase dispersion, are mathematically linked. You can derive one from the other.
Ah, so by adding Kramer's Kronig as a constraint.
They force the neural network's output to respect causality. It can't just find any solution that fits the data. It has to find a solution that corresponds to a physically realizable acoustic system. It dramatically prunes the search space during optimization.
Wow, okay, so it's not just fitting data, it's learning physically plausible behavior.
Exactly. It elevates the model beyond just being a fancy curve fitter. It becomes genuinely physics aware.
And the results reflect this. The numbers look pretty good.
Yeah, the metrics are strong. Over 39% reduction in magnitude error, and importantly, over 51% reduction in phase error compared to the baselines.
That 51% in phase seems like the key metric here.
I think so. Because, like we said, accurate phase, especially low-frequency phase, is what gives you sharp spatial localization. Getting that right is huge for creating convincing spatial audio, and the fact that it performed well on two different car datasets, the BUCK and Tesla datasets, adds confidence.
Okay, so what are the caveats? It relies on measurements inside cars. How far does this idea stretch? Could you use INFR for, say, a concert hall?
That's the big question. The core principle of modeling implicit frequency response fields should generalize, absolutely. But the current model is trained specifically on data from car cabins.
Right.
The acoustic behavior, the modes, the boundary conditions in a small enclosed car are wildly different from a large reverberant hall. So generalization beyond cars hasn't been proven yet.
And practically speaking, how fast is it?
That's the other potential hurdle. Implicit neural fields are powerful for modeling, but querying them, actually calculating the frequency response for a specific point or direction, can be computationally intensive. Getting this to run in real time on, say, the kind of embedded processor you'd find in a car's infotainment system, that might be challenging. Latency could be an issue.
So scientifically sound, a really promising direction, but maybe needs some engineering optimization for real-time use.
That's how I see it. It's a research breakthrough showing a better way to think about modeling acoustics, especially leveraging the frequency domain. The next step will likely be finding ways, maybe through model distillation or clever optimization tricks, to make these queries fast enough for practical real-time audio rendering.
Okay, our third paper pivots again, this time into healthcare. Clinical speech assessment. The paper is XBPG-PCA, reference-free automatic speech severity evaluation with principal components.
A crucial area.
This comes from Bence Mark Halpern and an international team, including folks from Japan and the Netherlands Cancer Institute. Published October 2nd, 2025, in IE Selected Topics in Signal Processing.
And this one tackles a massive challenge in speech pathology. Assessing how severe a speech disorder is, maybe after surgery for oral cancer, like a laryngectomy, or from a condition like dysarthria, it's usually done by trained clinicians listening.
Which is subjective, takes time, costs money.
Exactly. And the automated methods developed so far, They typically need one of two things that are hard to get in the real world. Either full, accurate transcriptions of the speech.
Which is expensive itself.
Right. Or they need a collection of recordings from healthy speakers to use as a reference point for comparison.
And finding good, comparable, healthy references for every specific condition, especially rare ones, must be incredibly difficult.
It's often impossible. So the need for something objective, quick, and crucially reference-free is just enormous for clinical practice.
So how does XBP-PCA achieve this reference-free assessment?
Their approach is really quite elegant because the core learning is unsupervised. As they lay out in Section 5, they don't try to compare pathological speech to healthy speech. Instead, they take a corpus of only pathological speech in this case, from the NKI-OC-VC corpus of Dutch oral cancer patients, and they look for the main directions of variation within that pathological data itself.
So they're not asking, how is this different from normal, but what are the main ways these pathological voices differ from each other?
Precisely. They're learning the inherent structure of the pathology's severity directly from patient data.
Okay, let's break down the input features they use. It's a combination of X vectors and phonetic posteriorgrams, or PPGs. What does each one capture?
This is a smart choice of features that capture different aspects.
Right.
X vectors. You usually hear about them for speaker AD, right?
Yeah.
But they're also really good at capturing overall voice quality. Think of the X vector as encoding the stable acoustic characteristics, the hoarseness, the breathiness, the vocal tremor, the sort of long-term acoustic signature related to the physical state of the vocal tract.
Okay, the texture of the voice and the PPGs.
Phonetic posteriorgrams are different. They capture the timing and articulation. They essentially map the speech signal onto probabilities of different phonetic units over time. So if a patient has slurred speech or inconsistent timing or trouble forming certain sounds, the PPG sequence will reflect those deviations from typical linguistic flow.
So you get texture from X vectors and timing or rhythm from PPDs, a holistic view?
Exactly. Orthogonal features covering different dimensions of the problem.
And then they apply principal component analysis, PCA, to this combined feature space. Why PCA? Not, say, a deep neural network classifier.
Good question. I think it's deliberate for two main reasons. First, PCA is very efficient at finding the directions of maximum variance in high-dimensional data. It's mathematically straightforward. Second, and this is absolutely critical for clinical use, PCA is interpretable.
Doctors need to understand why the score is what it is.
Exactly. When they run PCA on these combined features from the patient corpus, the resulting principal components, the main axes of variation, turn out to naturally correlate very strongly with the clinical severity ratings assigned by experts. So a clinician doesn't just get a single severity number, they get components. Maybe PC1 relates more to voice quality issues from X vectors, and PC2 relates more to timing issues from PPGs.
Yeah.
It provides an interpretable basis for the severity.
The transparency is definitely key for adoption in medicine. How well did it work? They tested it on 3 Dutch oral cancer data sets.
The robustness looks really impressive. They reported correlations higher than 0.8 with the expert clinical scores on multiple data sets.
And R.8 is considered pretty strong in clinical research, right?
It's very strong. It basically means this completely automated, reference-free system is performing on par with, or even better than, subjective human raters in terms of reliability and consistency.
They also showed it was stable even with noisy recordings.
Yep, stable across different signal-to-noise ratios, which is vital. Clinic recordings are rarely pristine.
And they did that shortcut analysis.
Yes. Section 6.1, this is clever. They specifically checked if the model was just latching on to simple things, like how long the recording was or how fast the person spoke, or the noise level things that might accidentally correlate with severity but aren't the real pathology.
And
they found those potential shortcuts didn't generalize across different test sets. That gives you much more confidence that the PCA model is actually learning features related to the underlying speech pathology itself, not just taking superficial shortcuts.
okay, but let's look at Table 2 again. The performance seems mixed depending on the type of disorder. Great for voice disorders, laryngectomy correlations over 0.85, but for dysarthria, it drops way down to 0.44.
Yes.
If the goal is a general severity tool, doesn't that significantly weaken the claim? It seems very good for some things, but not others.
That's absolutely the right point to raise and a necessary caution. It does highlight a limitation in its current generalization, but I wouldn't say it undermines the core unsupervised principle. What it suggests is that this specific combination of features, X vectors and PPGs, and the PCA basis learned from that NKI oral cancer corpus. It's very well suited for capturing the kinds of voice quality and articulation issues common in laryngectomy or certain voice disorders.
But not the issues in dysarthria.
Apparently less so. Dysarthria often involves more complex issues with neuromuscular control affecting prosody, rhythm, and maybe specific phonetic distortions in ways that aren't fully captured by standard PPGs or the overall voice quality and X vectors.
So it's like they've built a really good tool for specific types of problems, using a general framework.
That's a good way to put it. For dysarthria, they might need to bring in different or additional features, maybe something explicitly targeting prosodic variation or more detailed phonetic analysis. The takeaway isn't that unsupervised PCA is flawed, but that the feature engineering still needs to be informed by the specific pathology.
Got it. And other limitations. It's Dutch-specific for now.
Right, the immediate use is limited by the language focus of the training data. And while it's reference-free regarding healthy speakers, it does rely on those pre-trained X-vector models. So if the underlying X-vector model changes, you'd likely need to rerun the PCA and recalibrate the severity mapping. It's not entirely dependency-free.
Okay, so pulling back and looking at VoxCPM, INFER, and XPPG-PCA together. The big theme this week really feels like this successful push towards embedding deep domain knowledge. These aren't just black boxes. They have structure informed by the problem itself.
Absolutely. That structural intelligence, I think, is the key to their robustness and potential longevity. And each paper does it differently, right?
Yeah.
You have VoxCPM using hierarchical modeling and that FSQ regularizer to bake in linguistic structure, separating meaning from sound.
You have INFER embedding acoustic physics, literally using Kramer's Kronig constraints to make sure its predictions are physically possible.
And XPPG-PCA leverages clinical insights about relevant features combining voice quality and timing, and then using PCA to find an interpretable structure related to severity.
And a major practical outcome of adding this domain knowledge seems to be getting rid of dependencies on external references.
Huge. That trend towards reference-free systems is a massive practical advantage.
How so across the three?
Well, in TTS, VoxCPM ditches the need for external tokenizers, making the system more self-contained, less brittle.
Right.
In acoustics, INFR learns the response directly from measurements, removing the need for detailed geometric models or complex, potentially inaccurate simulations.
And in the clinical space.
XPTG-PCA works without needing those healthy reference samples, which, as we said, is often the biggest blocker to using automated tools for many conditions. The field seems to be maturing past methods that need perfect ground truth or ideal reference points.
What's also interesting is that even though these are end-to-end trained, highly optimized systems, they manage to keep a degree of interpretability. That's often the first thing to go in deep learning.
Yeah, that balance is crucial, especially for getting these things adopted and trusted. VoxCPM's hierarchy is interpretable. TSLM for content, Realm for acoustics. INFER, working in the frequency domain, makes spectral effects and phase shifts explicit. You can see the acoustics. And XPPG-PCA, with its PCA basis, lets clinicians connect the dots between the score and specific types of vocal variation.
Okay, so if these domain-aware, reference-free, interpretable models are where we are now,
Yeah.
what's still missing? What's the next big hurdle for audio ML based on these papers?
I think the big missing piece is true cross-domain generalization. We saw it with XPPG-PCA, right? Great on voice disorders, less great on dysarthria.
Right.
VoxCPM is currently limited by language. INFER is specific to the car cabin environment. Each system achieves its robustness partly because it's highly specialized. Its deep knowledge is narrow.
So the specialization is both a strength and a limitation.
Exactly. The real challenge now, I think, is figuring out how to take the principles learned in these specialized models and combine them. How do you get the disentanglement smarts from VoxCPM into a clinical tool like XPPG-PCA? How do you apply the physics-informed constraints from INFER to make generative models like VoxCPM more physically grounded?
We're not yet seeing truly universal audio models that can handle synthesis, perception, physics, pathology all equally well.
Not yet. We have these brilliant specialized blueprints. The next frontier seems to be about integrating that structural intelligence, figuring out how to fuse the domain knowledge from these different areas without losing the robustness that specialization currently provides.
So it's less about just scaling up, more about scaling smarter by combining these architectural ideas.
I think that's exactly right. It's about combining these different forms of structural intelligence. Hashtag outro.
Well, this has certainly been a thought-provoking week in audio ML. Really highlights the power you get from specialization and embedding real knowledge. For everyone listening, researchers, practitioners, the takeaways seem pretty clear. Embrace hierarchical modeling for disentangling information. Consider frequency domain processing when spectral accuracy, especially phase, is paramount. And definitely look towards unsupervised interpretable methods like PCA when you're in domains with scarce labels or where trust and understanding are critical, like healthcare.
Absolutely. These papers are really setting a higher bar for what makes a deep learning model truly useful and trustworthy. It feels like the future belongs to models that bake in verifiable domain knowledge but are still trainable end to end. So maybe a final thought for you to chew on this week. We talked about three key advances: physics constraints ensuring causality, semi-discrete representations for disentanglement, and unsupervised PCA for interpretable severity. Each one solves a specific kind of dependency problem on physics, on tokenizers, on healthy references. Now, if the next step is to combine these ideas, where do you think the most powerful integration point will be? Will the breakthrough come from a better foundation model that learns the physics of sound deeply, like INFER hints at? Or will it come from a more universal way to model high-level intent and causality, like the TSLM and VoxCPM, that can then be applied across different audio tasks? Where does that structural integration start? Something to ponder.